distance we have computed for u so far, plus the weight of the edge from u to v, right? And we take the minimum across all of the patterns of v, and now that should be the minimum distance to v, right? So the only difference between this and Dijkstra's algorithm is that in this case, we don't have to keep doing this many times, because we know the time to check this is when v is being output by the topological sort. Okay, at that time, the weight of the path to all of its parents is fixed, right? In the case of Dijkstra's algorithm, we perform this update many times, because but when we do this update, after that the shortest path to u may change. Okay, because we don't know, we have s here, right? So we may come to u right? We may come to s through this path to u, and at that time we might update the weight to v, or we might come through here on another path and update the weight. Whereas here we know that the only time I need to worry about the path to v is after all of the patterns have been done, right? And then I just do, in one step, I do this update, and therefore I do this. This whole thing can be done in how much time? What is the runtime of this algorithm?
Linear.
Linear meaning?
Number of edges.
Right. So that's all. I just wanted. So we can. The topological sorting will take order of e time. Now we go through each vertex, and then for each vertex we are going to look at its parents. So the number of such parents is going to be the sum over all the vertices of the number of their parents. That's exactly the total set of edges in the graph, and therefore this whole thing is going to take order of e time, right? So topological sorting is order of e, and shortest path, single source shortest path, is order of e, which is quite interesting, right? Because again, see, remember what we are doing here is computing the distance from S to every possible vertex, right? And all of that can be done in order of e time. Okay, so why DAGs in dynamic programming? I think we have already said that many times. So the nodes represent subproblems, edges capture dependencies between subproblems, and then topological sorting says, okay, in what order do you solve the subproblems so that the super problems are solved after subproblems. So Fibonacci is a very simple example of an algorithm that can be speeded up using dynamic programming, right? Because all you need is you know that f of I depends on, right? So you can arrange the numbers 1, so this is the DAG that is associated with the Fibonacci problem, and so you will evaluate f of 1 and then f of 2 and f of 3 and so on. Now anytime I guess I'm sorry, so I should say that, right? That is the dependency graph for Fibonacci problem, because f of 3, for instance, depends upon f of 2 and f of 1, right? So I have to have 2 incoming edges, right? The topological sort of this is just 1, 2, 3, 4, 5. So I have to solve them from left to right, and now I have a solution which now takes how long? Linear time, right? Linear time under what condition?
calculated order?
Well, I was just trying to see if you remember the comment we made long ago, which is that Fibonacci numbers grow very fast, and therefore to assume that addition is constant time is not a reasonable assumption. Anyway, that's sort of a different problem. So you can definitely think of Fibonacci, the recursive version, right? Repeats this many subproblems. So essentially repeats subproblems an exponential number of times, right? And so the non-memoized version of Fibonacci is exponential. But if you express the dependencies between subproblems and then solve them in the topological, in the order given by topological sort, then you can do it in linear time. Okay? So we'll do another problem which is called longest increasing subsequence. So we're going to spend a few lectures on dynamic programming, and the reason why I'm doing this is because dynamic programming is a very powerful technique, but it is also a bit difficult to wrap your head around. Okay? So what I mean by that is that it's easy enough to understand how dynamic programming works, and it's easy enough to understand how a given dynamic programming algorithm works. But what you need to be able to do, after doing a course like this is, given a problem where you can use dynamic programming to solve it, right? You should be able to apply dynamic programming, right? So that takes, more time, whereas greedy and divide and conquer are quite intuitive, right? I mean, this is not to say that every greedy or divide and conquer algorithm is so simple that all of us could invent them. But what it means is that where there is a way to apply these techniques, and it's not too difficult to see the connection, then you'll be able to apply it. Whereas in the case of dynamic programming, even that is a bit hard. That's why we'll use many examples, and hopefully by the time we are done with it, you might be able to apply it to solve some problems. Okay? So this problem is called longest increasing subsequence. So you are given a sequence like this, okay, and you want to identify a subsequence, right? So what is a subsequence? That means it's a subset of the elements here, but taken in the order, right? So for instance, 2, 3, 6, 9 is a subsequence, right? 5 is a subsequence, 5, 2 is a subsequence, 5, 2, 6 is a subsequence, right? But 5, 8, 2 is not a subsequence because you're not going in order. Okay? So the difference between a substring and a subsequence, you see that, right? Because in a substring, you can't have gaps. In a subsequence, you can have gaps, right? So 5, 2, 6 is a subsequence, but it is not a substring, right? So 5, 2, 8 is a substring, but 5, 2, 6 is not a substring. It's only a subsequence. So increasing subsequence means we need to get this thing done, set up right. Okay, so increasing subsequence means every successive numbers in the subsequence are in increasing order, and the question here is that what is the longest increasing subsequence? Okay, so that's what we want to solve. So let's try to represent this using a DAG. Okay? So what we are doing here is that we are connecting every vertex forward to every node that is greater than it. Okay? So 5 is connected to 8 and 6 and this 6, this 9 and this 7. Right? So that's why there are 5 edges going out of 5. Similarly 6, the greater numbers are 9 and 7, right? So we construct a graph like this, okay? And now on this graph, we can define the longest increasing sequence, subsequence problem, okay? It's a very simple problem, right? So we are going to compute the longest increasing subsequence going left to right. So what we are going to do is, let's assume that we have computed the longest increasing subsequence for all of these, right? Then we are here, right? What we are saying is that the longest increasing subsequence starting, that is ending at 6 is going to be obtained by going through the predecessors of 6, right? And then picking whichever one is the longest subsequence so far. So for instance, 6 has how many predecessors? So it's got 1, 2, and 3. Okay? So what we want to do is we want to go to this. Okay, so the length of the longest common sequence of 5, longest increasing sequence is just 1, right? Itself. Look at the other predecessor, which is 2. Well, again, the length is 1. And then you look at 3. Well, then you have 2 and then 3. So you have a length of 2. Right? So the longest increasing subsequence up to here is 2, 3, 6. Right? So what we do is we want to say, okay, what is the longest increasing subsequence up to here? And once you've computed that, then we compute the longest increasing subsequence up to here, and then up to here, and so on. Okay? So that's what this is doing, j equal to 1 to n. So it's starting from here, then j is going this way. And then what we do is, when you are at a particular j, you look at its predecessors, right? I comma j belongs to E means, right, I comma j belongs to E means I is the predecessor of j, right? And then we take what is the length of the longest increasing sequence up to I, and then we add 1 to that, right? And remember that the predecessor, because of the way we construct the graph, the predecessor is always less than j, right? Only then we have an edge. That's why we add the length 1 to say that j is being added to whatever is the longest sequence that we have computed up to I. Yeah?
So how do we construct this then?
We just go from 5, go through this, right? So this takes n square time. Is that if that's
You can construct it using a matrix.
right? So you go through, you start from 5 and then say, okay, which are all the elements that are greater than 5? You put an edge from 5 to that. Then go to 2, and then which are all the elements greater than 2, and put a arrow from there. Okay? So now,
We'll need some sorting.
No, it's like a matrix.
no, this is a sequence. The sequence is already given, right?
Yes, but I mean to get from each node to the nodes after it.
So you are constructing, so let's say you want to figure out what edges should go out of 5.
Yeah, so I have to go.
Yeah, you just go through linearly through this thing and put all the edges. Then go to 2, and then figure out which are all the ones that are greater, put an edge to them, right? So this is an n squared process, right? So is there a reason to think we can do faster than n squared? Let's ask this question. Let's say this is a random sequence, right? So how many, let's say this is a random sequence, and let's pick one of the elements, right? How many arrows can we expect to be coming into it?
At most.
Not at most, that's why I said random, right? Because if you say at most, of course, the worst case it's clear, right? If I give you 1, 2, 3, 4, 5, 6, then you immediately have an n square number of edges, right? But let's take a random sequence and let's ask what is the number of incoming edges to an element like this?
Like an average.
Yeah. What is the expected number if you want to be technical? So the calculation is simple, right? So for each number here, this number could be either greater or less, right? So basically it's like a 50% probability, right? Can be higher and or lower, right? Which means that you can expect generally of the order of n by 2 edges coming into each node, right? So n nodes, each of them having an average of n by 2 edges coming in, well, the graph itself, you can expect it to be of the order of n squared in size. So obviously you couldn't construct the graph in less than n squared time, right? Because if you're actually putting all those edges and there are n squared edges, well, it's going to take n squared time. Okay. So this is an example where it's already in topologically sorted order, right? Because we want to go from left to right in terms of subproblems are already, this is a subproblem and then this is a subproblem and this is a subproblem and so on, right? The subproblems are in that order. So the topological sorting is easy, and once that is done, we do a simple. So now, this talks about many of the common ways in which these dynamic programming, the substructure of the problem that frequently occurs in dynamic programming algorithms. So case 1, the input is a sequence x1 to xn. The subproblem of interest is a prefix x1 through xi. Okay? So now how many such subproblems are there? Right? A string of length n has n prefixes, right? So a prefix of length 1, prefix of length 2, 3, up to n, right? So so the number of subproblems is therefore linear, right? So when you talk about a dynamic programming algorithm, the number of subproblems matters because very often you may have to look through all the possible subproblems before you compute the optimal solution to the current problem. So if you have a linear number of subproblems, you can expect, okay, maybe I can do a linear time dynamic programming algorithm. But if I have a quadratic number of subproblems, then I'm going to need a quadratic amount of time. Okay? So in this case, you have the input consists of two strings, x1 through xn, y1 through ym, right? Maybe a string, maybe a sequence, maybe a vector, right? But essentially, for complexity purposes, you can just think of them as strings, right? So now, the subproblem consists of a prefix of x and a prefix of y, right? So there are obviously, nm combinations, right? So x has, there are x has length n, y has length m. So the number of prefixes of x is n, the number of possible prefixes of y is m. So if every possible combination corresponds to a subproblem, then there are mn subproblems. So you'll have a dynamic programming algorithm that at least has O of mn complexity. Okay? Sometimes the subproblems correspond to a substring. Okay? And what are the possible number of substrings? N squared, right? Because it can start, the substring can start in any of the positions 1 through n, right? It can end in any of the positions 1 through n. So each such combination, leave alone those cases where the end is before the beginning, right? So that rules out half of the possible cases. But still, you can say there is O of n squared, right? Because for every beginning and every end, there are n squared possible such combinations. So if the subproblems correspond to substrings, once again, you'll have O of n squared. Okay? And then the last case is where you have a tree and the subproblems correspond to subtrees, right? And then how many subtrees are there? If a tree has size n, how many subtrees are there? It's not a hard problem, right? I guess it is confusing. How many subtrees does a tree have? right? That's it, right? Each node defines a subtree below it. So if there are n nodes, then there are only n subtrees. So yeah, so if you have a problem where you're talking about subtrees of a tree, then it's still linear. So now we'll define the sort of the canonical dynamic programming problem, which is a subsequence. Okay. So remember, this is not longest increasing subsequence. We are talking about given two strings A and B. We want to find the longest common subsequence. So what is a subsequence? Well, we already defined what is a sequence and said how a sequence differs from string, right? A subsequence means that's something that we already defined when we talked about longest increasing subsequence. Well, we already defined subsequence. What is a common subsequence? Well, it's a subsequence that occurs in both strings, right? So B, D, E, F, H, J is a subsequence of this. So B, D, E, F, H, J, right? So the first string, string is a subsequence of the second string. Okay? So what is the longest common subsequence? It is the longest of the common subsequences, right? So you take all of the subsequences of X and all of the subsequences of Y, right? You take the intersection of those subsequences, so that will give you all common subsequences, and then you pick the longest one among them. Okay? And so what we want to do is we want to compute this longest common subsequence. Okay? So given these two examples, right? These two strings, then BEJ is a common subsequence, right? Which, by underlining, I've shown that they are common. Because, yeah, HJ. Okay. So here is another example, right? So X and Y are being compared, and you want to find the longest common subsequence, right? And one way to understand this is by arranging the characters this way. So this is this is X and this is Y, and you can see that a new character that was not in the originals in X has been inserted into Y, so we call it as an insertion. And here, a character that was in X is no longer here, so we talk about that as deletion, right? So insertion on X is the first string, so we talk about insertion and deletion with respect to X. Okay? So, and then you identify the edit operations. So the longest common subsequence, you identify the edit operations. Now, so the edit distance is a concept very closely related to longest common subsequence. So given sequence X and Y, what you want to do is you want to define a cost for insertion, deletion, and substitution operations. Okay? So here, in the previous slide, we showed three operations. Here is an insertion, here is a deletion, and here is a substitution. Okay? So we can assign costs for each insertion, deletion, and substitution operation, and then say, okay, tell me, what is the edit distance between these two strings. What that means is that so we talk about, when we talk about edit distance, we talk about a sequence of edits that you perform on X in order to get Y. Okay? So you have to do an insertion here, a deletion here, and a substitution here, right? So you apply those 3 edit operations, then you get the string y from string x. Okay? Now edit distance is a number of such operations that you have to do, and since there can be many edit sequences that can generate y from x, a trivial one is delete all of the delete all of the characters in x and then insert all of the characters in y. Right? That's a trivial way to construct any y from any x. Right? But the number of edit operations there is going to be the length of x plus length of y, right? Which is large. So the edit distance then is the smallest number of edit operations that generate y from x. But we don't say smallest number because we can actually associate a cost with each insertion, deletion, and substitution operation. And then we can talk about what is the lowest cost edit sequence, right? What is, we can instead of talking about the number of inserts, deletes, and substitutions, we can say each insert costs, certain amount, each deletion costs certain amount, and each substitution costs certain amount, and then you add up all of these costs and then tell me, okay? So it's an algorithm with a very wide range of applications. Spelling correction, right? So when you get do a spell check, underneath there is a edit distance calculation being done, and what is being suggested as a correction are correct words or words in a dictionary that are at the smallest edit distance from some word that you have typed in that's not in the dictionary. Okay? Diff is a program that presumably all of you have used, and it is based on edit distance. We'll talk in a fair amount of detail about diff. In the context of version control, your Git and SVN and many other systems are based on edit distance, and also it has a lot of functionality in a lot of use in sort of talking about understanding DNA, and for instance, if you want to construct an evolutionary tree, right? So you have a bunch of species, and you want to say what species evolved from which other species, right? So what you can do is you can take their DNA and represent the DNA as a very long string, and then you can compute the edit distance between the DNA of every pair of species, right? And then you can construct a graph that has this information, and then from that you can construct the likely evolutionary tree, which will be characterized by edges that correspond to sort of the lowest, smallest edit distances, right? Because when you have evolution, you think that species A evolved from species B if you can see that A had just a few edits to the DNA as compared to B, right? So this edit distance algorithm is something that has a very wide range of applications. So we'll talk about that in the next lecture. Okay, so we'll stop here, and